Hey, it's Jim, and this is FRM Part 1, topic on quantitative analysis and the lesson on sample moments. There are 4 sample moments, but I found it interesting that in the first sentence or two of this chapter, Garp tells us that the first moment is going to be of particular emphasis, but I didn't quite get that as I read through the chapter, and you'll see through these learning objectives, that first one, there's the mean, that's the first moment. There's standard deviation, that's the second moment. So I guess what Garp is referring to is that these first handful of learning objectives do, in fact, relate to the mean, but I'm not quite sure that the substance of the chapter relates to just that first moment because, well, there's Skewness, that's the third moment, and there's Kurtosis, that's the fourth moment. And then look down at the bottom. We'll talk about correlation, Coskew, and Cokurt as we end this slide deck. So I'm going to go ahead and try to emphasize all 4 moments, but you might want to pay attention to what Garp says in that first sentence or two. I'm guessing that you guys probably know the difference between a population and a sample. I'll give you just a quick example. There are probably 6,000 or so colleges and universities in the United States. I would have no idea how many finance PhDs teach at those places, but let's just say 1,000. And you want to study something like, hey, how many finance PhDs out there that are, what are their characteristics? Maybe like an IQ, or maybe whether they like golf, or whether they're very good at long distance running. I mean, however you want to study them. So if you want to study the population, you got to go out and interview all 1,000 of these people. And that just takes too much time and energy. So what you do is you take a sample. So you get some kind of random number generator out there, and you say, all right, I'm going to interview these 42 people, and they're going to be a cross section throughout the country, et cetera, et cetera. And so you take a sample. And so look at that little illustration down at the bottom right. There's the population. That's all 1,000 finance PhDs. And there's just a little sample. And I may or may not be inside of that sample. So the thing about this is that you want to select a sample that is reflective of the population. Like if you went and said, I want to study the IQs of finance PhDs, and I'm going to go ahead and sample only those who teach at Ivy League schools. Oh my gosh. Well, then you'd get probably an incorrect or an inaccurate description of the IQ, especially because I would be left out. I would be left out of that sample. Anyway, the idea here is that the sample has the same distribution as the population. Here's another example about S&P 500 stock returns for all trading days, which is, somewhere around 250 trading days. So the true daily return, that would be the population mean. But if we take a random sample of 30 days, now it's important to have a random sample because, let's forget about 2024. Let's go back to 2020. Suppose that you randomly picked, and I can't remember these dates exactly, like March 6th and 7th and 8th and 9th and 10th. Whenever the stock market crashed after COVID, after we shut down the economy here in the United States, if you put those days in there, well, you're going to have, some kind of a biased results. Now, the idea here is that if you take lots and lots of different samples of 30 days here, 30 days there, and by the way, they don't have to be, like January or July, just pick 30 days out there. What's going to happen is that the 4 moments, those samples, the more samples that you take, they're going to look an awful lot like the population. Notice the word down there at the bottom, we call that converge. An estimator is a statistic. That's the best guess. So, that in that previous example, the average return, that's going to be the point estimate, and the return, that's going to be the estimator. I'm not quite sure what that box tells us down there. I have no idea how to cook. I do know how to read. An estimator is like a recipe in a cookbook. An estimate is like a cake baked according to the recipe. I guess that makes sense. Maybe if my wife were here, she'd be able to explain that to me. All right, so here's a summary of this process. So remember that we've got this this population, whether it's stock returns or finance PhDs, and we don't know what we don't know what it looks like. So there's the unknown parameter, and there's just the Greek letter theta up there. It could be any Greek letter. We try to figure out what that probability distribution is ahead of time, but we don't really know what it is. We might have some idea of what it is, but we don't really know exactly what it is. So we collect a bunch of data. We collect, 30 days of stock returns here, or 27 professors that teach in the state of Michigan, or however that is. We collect that. And notice over on the right, there's some probability theory out there. And then we make an estimate. So notice that unknown parameter at the top, that's theta. And then the estimator down at the bottom has a little hat on the top. And that hat is tells us that, we really don't know what the population is, but we think we can have a really good idea of what the population looks like because we're taking the sample and we're going to estimate it with that estimator. And that's the best guess. So remember, when you're looking at a question stem on the exam, if you see just theta, that's the unknown parameter. If you see theta or any other Greek letter with a little hat on top, well, that has to relate to the sample. Now, remember when I said just a moment ago, if we took just the Ivy League schools and we use that as an estimator, well, that's probably going to be biased because it's not going to reflect the true population for those of us who don't teach in Ivy League schools, or for those of us who don't have PhDs from Ivy League schools or Chicago or Stanford. You got to take the high and the low. What did I say? IQ, or how we're going to measure that. Now, the idea here about unbiased is that if we expect that estimator with the hat on top of it, if we expect that to be identical, there's an equal sign there, identical to the true population parameter, well, then we say that it's unbiased. Clearly, that if you take 40 finance PhDs from Ivy League, that's probably going to be biased because those men and women, I'll say it, they're probably smarter than I am. They might not be more fun than I am when teaching, but they're probably smarter than I am, and that's okay. But if you take a random sample of all 50 states in there, you'll probably get an unbiased estimator. So what we want to do is we want to decide what, if there is any, what is the measure of the bias? And that's the second red block down there. All we're doing is taking the expectations of that sample estimator, sample mean, let's say, of an IQ, and we subtract out the population. And so this is really just kind of a theoretical graph down there because remember that population it's unknown. We really don't know. We might have an idea, but we don't know. All right, I'm guessing you learned this back in kindergarten, how to compute the mean. All you do is take a bunch of numbers and sum them. There's the sigma sign from I equals 1 to n, and then you divide by n. That's pretty obvious there. Look down at the bottom. The sample mean is in fact an unbiased estimator of the population mean, and that of course is depending on if you form the sample in the appropriate way. Now, a little bit later on, I'm going to show you some cool steps on the HP12C calculator, but here is scores of FRM candidates in a mock exam. So that's, remember, you have 100 questions, so 4 people scored 60, 3 people scored 64, 268, 172, 175. And by the way, when I took the part 1 exam, I took, I don't know how many mock exams that I took over the course of the last month beforehand. I probably took, 20, and my scores, they were all over the place. I remember taking one exam and I made like 52 out of 100, and I went to my wife and I was like, I'm an idiot. And then I took one and I made like 81 out of it. So who knows what those mock exams are really, really important though. All right, so you can calculate 65. I'm going to show you a little bit of a longer way on the 12C, but you'll appreciate that in just a second. When I was in graduate school, I had a couple of econometrics classes taught by just a stud of a professor. And one of the first things he taught us in that first class was this estimate has to be blue. That's the best. It's the best. I'll show you what that means here in just a second. It has to be linear and it has to be unbiased. So we talked about that, and that's the estimator. So blue, there are the conditions. This is a good exam question. Has to be linear, has to be unbiased, and has to be efficient estimator, which means that, imagine a graph where you have just a bunch of stuff in there. Who cares what the X and Y axes might be? And you just have a bunch of points in there. And so if you want to draw a line, what you want to do is you want to minimize the distance between all of those points and that line, or in that middle point. And so think of it as a vise. And so this blue estimator gets the vise, and it just squeezes and squeezes and squeezes until, look in parentheses down there, it has the least variance. Now, what's the usefulness of this? Because if you look at this illustration on the bottom right there, notice we have sample size from 0 all the way out to 1,000, and then there's some mean over there on the vertical axis. So when you have 1, or 2 or 3 observations all the way out to, whatever that number is. I mean, look how far away from the true mean of 5% is. But as you get out to 600 and 800 and 1,000, notice that difference is, that it's minimized, right? That's what that means. Look down at the bottom. Sample mean approaches the true mean with more data. So if you go out to 1,000, who the heck wants to go out and interview 1,000 finance professors? Yes, it must be unbiased or asymptotically unbiased. So that asymptotically word, that's a calculus word. It's an econometrics word as well, is that, if you picture some kind of a nonlinear relationship, and then you draw a line, and that line gets close and close and close to the curve. Here's the curve. As soon as it gets pretty close, there you have the asymptote. The estimator's variance approaches 0 as the sample size increases. That's going back to here, that if we went all the way out to, 10,000 or 5 million or whatever that is, that we would hit that red dotted line. Law of large numbers, we'll talk about that here in just a second. It works under general, but not all distributions. Now remember, we love to deal with a normal distribution. And let me give you a hint here. Remember, a normal distribution, all you need is the first and second moment. There's no skewness and there's no kurtosis in a normal distribution. But life inside of the financial industry doesn't always follow a normal distribution. But a lot of the distributions are what I call nearly normal distributions, which allows us to, make kind of nearly normal distribution conclusions about our research. But some distributions, they look like that, and then everything is thrown out of the box. All right, about the usefulness here, guarantees accuracy. Yeah, we'll talk about blue. We'll talk about consistency as we move through part 1 and part 2, especially when we talk about things like value at risk and maybe expected shortfall. There's the example there, credit risk default data. Yeah, reduces estimation risk in valuation. Value at risk. Yeah, predictive and stable. Yeah. All right. Good stuff. So moving on to the second moment of the distribution, there's our little lowercase sigma. There, notice it has a little hat on it, so that's the sigma squared. And so I always tell my students that you can compute the mean of a sample, and then you can expect that to occur, but you know that you're not going to be 100% accurate. So standard deviation, and in this case the variance, the second moment of the distribution measures the degree of error. If you expect something to happen right here, and can you guys see my arms way out? Something happens within this range. Well, that's going to be a high standard deviation, and the mean was pretty useless when you're trying to figure stuff out. So remember that standard deviation is a measure of risk, and how do we compute that? Well, look inside of the parentheses. What did we do for the mean? All we did was take each xi, and sum them and divide by n. But now we're going to take the difference between each of those x's. What did I say? What was that number I gave? 42 finance professors out there, and we're going to subtract the mean, and then we're going to square it. Now, this will never be any question on the exam, but it might be useful to help you understand second and then third and fourth moments. The reason that we square it is just simply to get rid of the negative. And in class, I always have the students play along. I say, hey, let's count the number of steps that Jim takes. So I go standing right in front of them and I go 1, 2, 3, 4. And they all say, hey, Jim, you took 4 steps. And I say, all right, now let's go ahead and pretend, you don't have to do this, but pretend that you're closing your eyes and your ears. Count the number of steps that Jim takes. So I tiptoe and I go 1, 2, and then I reverse myself and go 1, 2, back to my original point. And then I say, all right, open your ears and your eyes. How many steps did you take? And they say, well, Jim, you didn't take any steps. So in order to compute this variance, we square it just to get rid of the negative. Now, back in the mean, we divided by n, and if we divide by n for the standard deviation, we go ahead and we compute a biased estimator. So look down at the bottom, we have to divide by degrees of freedom, the n minus 1. So this is a really good exam question. When you divide by n, remember it's biased. Second moment is biased. But when you divide by n minus 1, it is unbiased. That's a great exam question. So if we go back to that original example, what we can do is we can compute the difference between, so there's the xi minus the mean. Mean is 65, right? We did that before. Square it, and you do all that stuff. Here, let me show you how the chapter does it. So if you take each one, so there's 4 60s, right? And there's 3 64s and 2 68s and a 72 and a 75. Subtract the mean and then square them and then sum. There's the 270 at the bottom. So there you go. You got the 270 divided by, there were 11 of those, right? 11 minus 1, you get 27. Take the square root of 27 and you get 5.2. Now, you can do it this way. I'm going to show you a better way here in just a second. All right, moving on to the third moment of the distribution. So here, let me go back here real quick. So where was I? Here. So we've got xi minus the mean squared. So the third moment of the distribution, we're going to do the same thing. We're going to take xi minus the expectation or the mean, and we're going to cube it. Raise it to the third power and divide by the standard deviation raised to the third power. So this makes sense, right? Third moment of the distribution, you just raise everything to the third power. So you go through the same process that we just did. Instead of 2ing it, you 3 it. Now look in the middle. There's our normal distribution, the mean and the median and the mode. They're all the same number. But if you have positive skewness, you have the mean is over on the slope. If you have negative skewness, the mean is over on the, well, maybe just a little bit left of the peak. So this is a good way to remember whether there's positive or negative skewness. And so think about what this means. Estimate and interpret skewness and kurtosis. I'll show you how to do that in just a second. But I think the better exam question is to interpret. So when we have positive skewness, what does that mean? That means that we've got more positive numbers out there. Maybe this is daily stock returns. Negative skewness, well, that's more negative daily stock returns. And so imagine if we're computing something like value at risk when we have normal distribution in the middle, well, we can make some reasonable conclusions. But if we've got positive or negative skewness, we need to take a step back and adjust for that skewness factor. And of course, one way we do this is through expected shortfall. All right, so notice in the numerator there we have 894 divided by 11, and then there's the standard deviation cubed. Do you want to do this the long way? So let's take the 60s. There's the 460s and the 364s, etc. So do all that, and you sum them, you get 894. So there's the 894 divided by 11, and there's 0.578. And that is our measure of skewness. Now, do you want to see a shortcut here? I mean, you can do all that stuff. You can do all that. But what I want to do is I want to show you just a shortcut here. So the first thing is to find the median. So let's go ahead and put the 460s and then the 364 there. All right, so you have all those. So how many is that? That's 11. So when you have an odd number to find the median, all you need to do is pick the middle one. So you have 5 on the left, 5 on the right. So the median is 64. And so skewness, now this is a shortcut. So all we're going to do is take the difference between the mean and the median, multiply that by 3. So you will remember 3 for skewness is the third moment. Multiply by 3 and then divide by the standard deviation. And you get, wait a minute, what was this back here? It is 5.78 and this is 5.77. So be my guest. Remember that if you use this shortcut on the exam, note that you might not get the exact answer that GARP gives you as one of your 4 choices. But I can't imagine that GARP would say, okay, answer A is 5.78, answer B is 5.77, answer C 5.76 and 5.79, whatever that is. I would think they would be spread out just a little. So if you have plenty of time on the exam, then make sure you do it the long way so that you get the most accurate answer. But here, if you're pressed for time, it's probably an okay shortcut. Kurtosis then being the 4th moment of the distribution, you shouldn't be surprised. We're just going to do the same stuff, but we're going to raise this to the 4th power. And while, here, let me go back here. While skewness measures, do we lean to the left or we lean to the right? What kurtosis is going to do is it's going to ask us, is that, here, let me go back here real quick, look in the normal distribution, is that peak, is it higher or is it lower? And are the tails heavier or are they thinner? So the focus of kurtosis is in the middle and in the tails. Now, a couple of definitions, couple of words that you need to know. Look at the bottom. Leptokurtotic and platykurtotic. Those are the words that I learned when I was in graduate school, but apparently they've cut them off. So a distribution that has more peak is leptokurtic. It has less peak, it's platykurtic, and the normal curve is mesokurtic. So, if you want to go ahead and memorize all 3 of those words, that's probably a good idea. Now, I wish I could give you a shortcut to kurtosis. I can't. If you want to do this the long way here, you can do the same thing. Raise the difference to the 4th power. You get the 15,000. This is a really good example to teach you guys the long way. However, during an exam, I can't imagine that in one question, GARP would say, and remember now, GARP likes to ask 2 questions inside of one question, but I can't imagine that it would ask you for, hey, calculate the mean, standard deviation, skewness, and kurtosis all in one problem. If it does, then my advice is just to do it the long way. But if you get to a kurtosis and you get to something like this, remember this relationship here. kurtosis has to be greater than or equal to 1 plus the skewness squared. So our skewness was 577 or 578, whatever it was. So that comes out to be 133. So my advice is to say something like, okay, GARP is going to give you 4 choices. So if you do this here, you could probably eliminate 1 or 2, maybe even all 3 of them, so that you can do kurtosis, relatively quickly. So it's really up to you. I'm just providing you with, these, kind of shortcuts if you're pressed for time, which you probably will be. For those of you who watched one of my videos about me taking that part 1 exam, I finished the 100th question within the last, 90 seconds of the allotted time. So I was on time, but I didn't have any spare time. Now, you might remember that a couple of chapters ago, we talked about the quantiles. So this is pretty much a review. Remember that when we have these continuous random variables, then what we can do is we can assign some probabilities to them. And so if you look in the red box in the middle, if we have a continuous random variable, we can find a solution for the median. And so that median is 50%, right? Half on this side, half on that side. If in fact it's a normal distribution, then of course that's the mean is 50% this way and 50% that way. And then the quartiles, 25, 50, and 75, we can compute that interquartile range. And so there's a really super easy question at the end of this learning module that I want you to go over so that you'll be able to do that. This is what I was saying to you earlier when we did our 64 to calculate that median. So that was an easy one to do. But if there is an even number, so go back to that. Here, do I want to go all the way back there? Where was my... There we go. So imagine that there's a 12th one. Put a comma after the 75 and make it 77 or 78. How would you find the median there? Well, you'd get the 2 ones in the middle. In this case, it would be 64 and 64. So the median would still be 64. But if for some reason that were 64 and 65, then you'd add them and divide by 2. So let me go back to this. Where am I here? There you go. So the median for evens, and this is probably a good question on the exam. Just take the average. So it may or may not be an actual observation. That's the 64.5 that I was telling you about. Yeah, it's used when we need the midpoint. And that brings us to this thing that I was saying earlier. I said I'll mention this law of large numbers and the central limit theorem, which was developed by a Russian dude, Chebyshev, I don't even know how many years ago, in the 1780s or some really super long time ago. But if we have this law of large numbers, if we're doing a coin flip here, notice that, and this is what people do in Las Vegas or gambling, when you're playing roulette, they have the number. They have a sign there that says, hey, number of reds in a row, red, 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 black, 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 black. So that's why at 0, there's a huge discrepancy because, you can flip a coin and you could get heads, 5 or 6 straight times to start out with. But if you have 5 or 6 heads after the 1000th coin flip, it has much less of an impact. So that's all this graph is telling us. Now, what does this mean for all this stuff that we want is that, of course, if we have more observations inside of the sample, that means that our sample estimate is going to be more accurate. Now, of course, we call that a consistent estimator in the econometrics world. Here's this Chebyshev and the central limit theorem. Let me read that bold to you. The sampling distribution of the sample mean. All right, so you've got this population of 1,000 finance PhDs. If we take a sample of 42, Well, we're going to have some sample distribution that may or may not be normal. Just with those 42, it probably would be because it's over 30. But if the population is normal, I guess I should add to that. But as we add, if we go up to 62 and then 82 and then 102, we're getting closer and closer, right? The large numbers, we're getting closer to a large number. That sampling distribution is going to be, and this is what econometricians say. They say it's approximately normal. I use the term nearly normal. So look at the bottom box. Distribution, it tends toward normality, which, as I said before, means that we can use the normal distribution and make conclusions based on it with the idea that, you know what, it's nearly normal, so we're not going to be perfect, we're not going to be 100% accurate, but it's better than nothing. Yeah, my professors back in graduate school, they really harped on this idea of 30. So look in the far right there. It must be at least 30 before the distribution becomes approximately normal. But my econometrics professor, he pretty much didn't let us get away with collecting a sample of 30. In fact, when I wrote my dissertation, I looked at, I don't know, maybe 2,000 different companies. I calculated 2,000 betas and all sorts of fun stuff out there. But the idea here is that when we get to a large enough sample size, we're going to hit that normal distribution. And so here's a picture of a nearly normal distribution. I mean, you can see the red, that's perfectly normal. But if we're doing monthly stock returns, we're going to get nearly normal distribution. And so, look at the tails. This is important. The tails, it's nearly normal. Think about trying to compute a value at risk or an expected shortfall over at that left-hand tail, 95%, 99%, whatever you want to whatever you select. Look at the bottom. It's key for risk quantification. There you go. Value at risk, expected shortfall, and stress testing. Now, what if we have two variables? What does this mean for large numbers and the central limit theorem? So here's the example that we came up with. Let's suppose that we've got two variables, x and y. Let's call them stock returns. Let's call them bond returns. Now, what do we know? We know from history and just maybe common sense that stocks have greater risk, so therefore they probably have greater first moment of the distribution than do bonds. What we can do then is we can take the mean of the stocks, we can take the mean of the bonds, and we can throw them into a matrix. Now, if we just have 1 by 2, we call that a vector. And we have the mean of stock returns and the mean of bond returns. Okay, so this is called a bivariate statistic. So remember, back in book 1, we had this chapter on risk data aggregation. Of course, back then we had a conversation on throwing multiple variables inside of this. So imagine a vector of stock returns and bond returns and credit default swap returns and option returns and think of this big vector. And what we're trying to do is aggregate this data and use it in the most efficient possible way to try to make some kind of a prediction. What we're going to do is we're going to make a prediction based on those two, in this case, stocks and bonds, not just stocks only and bonds only. We're going to combine those two. Now, what happens is that you get this big elliptical, and this is true not just for stock returns and bond returns, but anytime you throw this bivariate process together, this normal distribution looks like that thing there, and there's the big old X right in the middle, and that's where the mean X and the mean Y, the mean stock returns and the mean bond returns, that's where that falls. So think of this elliptical thing as kind of a joint normal distribution. What we can do is this adds value to our ability to manage risk and make predictions. Yeah, here's just a quick example here. comparing Russell 2000 with some bond index there. So 10 versus 6, stocks have higher returns. Variance 335 to 25. There we go. That's way more risk. I mean, the risk of bonds is this big. The risk of stocks is this big. Covariance is 14. I'll talk about that here in just a second. And correlation coefficient is 0.15. So it's positive, but it's not very strong. Now let's go ahead and ask the question that sounds something like, all right, we've got a sample mean for stocks, a sample mean for bonds. What can we do? We can compute that correlation coefficient between, which we did down at the bottom there. What was that? 0.15. And we can use that to help us diversify our portfolio of stocks and bonds, but we can also use correlation coefficient to add diversification to our financial institution. I mean, there's a correlation coefficient between, let's say the ATM silo and the derivatives trading desk. There's a correlation coefficient between those two, so that the chief risk officer will know what that number is to better manage not only the individual risks, but the enterprise-wide risk of the financial institution. The point here, look down at the bottom, you can't ignore correlation. So this law of large numbers, that's great. When you go way out there, you have just a little bit of a difference out there. But don't let GARP fool you on an exam that says something like, oh, we did stocks, we did bonds, we did 1 million in the sample of each of those, and therefore correlation coefficient doesn't really matter. So don't fall into that trap. Yeah, this is just a quick two graphs that show the relationship between the returns, the actual raw returns over on the left, and then the mean pairs of returns over that sample there. All right, let's spend a little bit of time talking about correlation and covariance. I tell my students this all the time. In fact, we calculate this in Excel fairly regularly. You can calculate the correlation coefficient between two random variables like stocks and bonds, or stocks and alternative investments, or stocks and inflation, or stocks and the number of clouds in the sky. And when you compute the covariance, you might get a minus 485. You might get a minus 0.267. You might get a positive 857. So when you look at that number, that covariance number, you have to scratch your head and you have to say, gosh, what does that mean? How do I interpret that? Well, it's tough to interpret a covariance. That's why we standardize it. We take the covariance, put that in the numerator, and we divide by the product of the two standard deviations. We standardize it, it becomes a correlation coefficient, which we know has to be between a -1 and a +1. Then we can wrap our hands around that and make some kind of a reasonable conclusion. So that's really important. The difference between covariance and correlation coefficient is correlation coefficient is a reasonable, highly interpretive term. However, notice that the learning objective asks us to estimate covariance between two random variables. So how do we do it? Well, remember back with variance, we took the difference between each outcome and the mean and we squared it. Well, now we're going to take the difference between each outcome and the mean of the first variable and multiply it by each outcome of the second variable and its mean. So we're not really squaring it, but we have a product. That's why we call it covariance. We call it variance because we're squaring it. We call it covariance because we're considering two variables. So the interpretation, or at least the loose interpretation, is that when you have a positive covariance, you've got variables moving together. And if you have a high covariance, that means that they move together in a strong fashion. Now, what we can do is get this sample covariance estimator. This goes back to what we did in the very first 10 minutes or so of this slide deck. And all we're doing in the orange is we're just doing the same thing that we did. the sample covariance estimator is known to be biased towards 0. So that's an important one, which means that they're offsetting stuff. Positivity and negativity offsets. Now look down at the bottom. We need to divide by n minus 1 again. Notice up at the top, we're dividing by n. So the conversation that we had with the biased versus unbiased, divided by n minus 1 for variance, that applies here as well. Let's go ahead and take a look at an example. Let's go ahead and compute not just the covariance, but I'm also show you a shortcut to calculate the correlation coefficient. But let's go ahead and look at this as if GARP has given this to us on the exam. So we have stock 1 returns, stock 2 returns over 1, 2, 3, 4, 5. They could be days or weeks or months. So how are we going to compute the covariance? Let's go ahead and do this the long way, like the chapter describes. Now, notice up in the top box, I have the average return and the standard deviation of the return for stocks 1 and 2. So let me show you how to do this in a super fast way on the 12C. And by the way, this I'm doing some artificial intelligence stuff in my class. So this box was generated by some artificial intelligence on Google. So I'll make sure I give credit for that. Although I could have easily made one up. I did all these calculations myself. So you ready? Let's do this. So I need to go back to this one here. All right. Now, in order to calculate means and standard deviations, we're going to need this enter button and the sigma plus button. So my advice is always to go like this, do a clear sigma, and then clear the register there. So you ready? So let's go ahead and do stock 1. So we're going to do 1.1 enter, 3 sigma plus. And it tells us that's our first entry of both. So we're just going to repeat that. Are you ready? We're going to do 1.7 enter, 4.2 sigma plus, 2.1 enter, 4.9 sigma plus, 1.4 enter, 4.1 sigma plus. Hold on, we're almost there. 0.2. Did I hit enter? I think I did. I'll hit it again. 2.5 sigma plus. So there are the 5 entries, right? We did both of them. So what we can do is we can do a see the blue here? There's an X bar and an S. So we can do a blue X bar. There's 374. That's for stock 2. And we can do, well, I can hit the XY. I'll get the other one, right? So there's the 1.3. Then I can do blue S. There's my 0.79. Then I can do XY. And there's my 71764. So remember early on in the slide deck, we did a mean and standard deviation. So feel free to do it that way. All you would do, you would just hit, what was that first number? 60. So you would just do 60 sigma plus and then 60 sigma plus, and then you would do the blue 0 and the blue dot. All right, so let's, so that's how we calculate the average and the standard deviation. So hopefully that was pretty helpful. And by the way, those of you who have the Texas Instruments calculator, it's a simple process. You're going to hit your second data button and you're just going to enter the X and the Y's. Let me go back here. Just enter the 1.1 and the 3.0, right? And then once you do that, hit your gold stat button and it'll come up LIN, and you just hit your down arrow and it gives you all that stuff. So it's easier for the other. It's easier in the Texas Instruments but I wanted to show you the 12C. All right, so let's get back to computing this covariance here. So notice in the second box, we've got the stock returns for stock 1. So there's the 1.1 all the way down to the 0.2. So we're going to take 1.1 minus the 1.3. So that gives us a minus 0.2, right? You do the same thing for stock 2. And then we have to take the product, right? Let me go back. Where am I going here? So there's the difference, x minus x, and then times y minus y, right? And so you do that and you get the product. And if you sum the product, you get 2.66. Divide by n minus 1, right? Divide by 4, and you get 665. There's our calculation for covariance. I'm going to come back to this here in just a second. But let's move on to the correlation coefficient. So what did I say to you earlier? Well, look in the purple. Here's the exact formula that I described. You take that covariance and you divide by the product of the two standard deviations. Notice in the blue box, we have the Greek letter rho, so that's the sign for correlation coefficient between x and y, and then we use our sigma hat, right? This is the sample stuff, and so there's our symbol for covariance in the numerator, and then the product of the two standard deviations. Since this is a standardized random variable, it's going to be squeezed or squoze, whatever the past tense is. It's got to be between a -1 and a +1. Now, the question becomes, how can we calculate that correlation coefficient? So I am going to go back here to this. Let's see if I can do this. So what we're going to do is we are going to, let me get my glasses down so I can see. I'm going to do a blue. Oh, no. I'm going to do a 1 blue, and then this little XR right there. And then I'm going to do the XY, and there's my correlation coefficient. Voila, as my mother used to say. My mother was an enigma. I had no idea what voila meant back then when I was little, and I still don't know what it means. Anyway, so there's a shortcut to compute the correlation coefficient. Now, here's my advice. Clearly you can go through this whole process to compute the covariance, and that's perfectly fine. However, my advice is to go ahead and compute the correlation coefficient, 954, just like we did. I mean, look, that's just 1, 2, 3, that's just 4 extra buttons on your calculator. And then use our equation to back in to the correlation coefficient. Because look, we already calculated the 718 and the 971. You hit 4 more buttons, you get the 954, so you can back into the correlation coefficient of 665. So instead of having to put together a big old table on the exam, you can just use your enter button, your sigma plus button, and then the 1G, XR, and X and Y. All right, we're finishing up here. Let's go ahead and look at how you can, if you can have correlation between stock return 1 and stock return 2, or in our earlier example, stocks and bonds, well, it makes sense that you can have Coskewness and Cokurtosis. So I always think of correlation, coskew, cokurt as measures of co-riskiness. Now there's an equation. Notice that the learning objective is explain and not calculate. So from my perspective, I would just throw out the purple, throw out that thing right there. But I think the bottom, this is important here. This is an application. This is an explain. If we have positive Coskewness, they're going to have extreme positive deviations, both at the positive end or at the negative end, right? Extreme positive deviations at the same time. With negative Coskewness, that just means the opposite. Extreme negative deviations at the same time. And we're going to have the same kind of interpretation for Cokurtosis. there's the purple. Do you really want to memorize those things? Do you really want to do that? I don't. So, oops, I went one too many. Get out your phone, take a picture of this thing here. This is the great exam question for Coskewness and Cokurtosis. And I believe that takes us through all of our learning objectives. We did a whole bunch of those. So let me ask you a quick question. Do you feel like we emphasized the first moment of the distribution over the other three? I'm not so sure we did. Just pay attention to those first 5 or 6 learning objectives, just because I think that's what Garth was hoping that you get out of this. But I think if you can do the 4-moment kind of calculations in the examples that I gave you, I think you'll be fine for these questions on the exam. There are 16 questions at the end of this chapter, so I want you to go through them. Only 4 or 5 are going to require the use of your calculator, but you'll get some good practice. So hey, as always, I appreciate your attention. I really do. Thank you so much for watching. I'm hoping this was helpful. Have a great day, and as always, good luck studying.